Okay, so we're back for the final part, which is number 2, or problem 2 of this same problem set. And then very similar to the first one, you're going to have a series of 3 lens of different base curvatures, and we're going to see what happens to the relative image sizes created by each. In this case, we're actually just transporting ourselves back into Woolston's day, Ben Franklin glasses, positive front and back base curvature, and we're going to have to do mathematical calculations just as we were doing with the first set. So let us get started. So in this case, it's a little bit, so we're going to talk about lens number 1 for the second problem set. So this is lens number 1. All right, and now for this set, the wording is a little bit different. They tell you that the back focal distance is 5 centimeters, and that's a fixed parameter. All right, so rather than giving you the back base curvature or the back vertex power, they're giving you the back focal distance, and they're telling you that across all these lenses, that is going to be 5 centimeters. Okay, well, so it's kind of weird. It's just different. All right, but the back base curvature, or the back vertex power, excuse me, is the inverse of the back vertex focal point. All right, so we're going to take the inverse of the 0.05, and that gives us a 20 diopter back vertex power. All right, so that gives us 20 diopters, and that's what we were working with in the past. So we're just one little more busy work to do so that we have values that we can use in formulas that we know. Once again, the thickness is going to remain constant across these thin lenses, and that is going to be the same 10 millimeters that we were talking about before. The index of refraction is not going to change across the 3 lenses. It's going to be a 1.5 index of refraction. And we are going to have a base curvature of the first lens, so the power of the front lens, or the front base curvature, is given to you as 0. Well, that's kind of queer. All right, what does that mean? Well, that means that I have a front surface of the lens that's flat, that it's actually plano, square like that. All right, and I know that the overall back vertex power is going to be 20, so I know it has to be a plus lens, so I know the shape is going to look like that. It's going to look like half a pie. All right, and so that's kind of kooky, but we're just starting with the flattest base curvature on the front, and then we'll incrementally increase that, and you'll see as we do the other problems. All right, so given that little oddity there, we're just going to accept it because it was given in the problem, and then we're going to figure out what our different powers is. All right, so I need to know what our equivalent power is, and so once again, that is related to the back vertex power, and its equivalent lens is related to the back vertex power by this ratio of the compensation factor and back vertex power. We're interested in the front base curve. All right, so this is going to be 0, right? So you know where this is going, but we're going to do the math anyway in case you didn't pick that up. So that's 20 diopters there. This is going to be the equivalent power here. This is 1 minus. This is the thickness. This is the indice of refraction, and the front curvature given to you in a problem is 0. Well, 0 times this is 0, so this thing all goes away. All we're left is the 1 in the numerator. So the equivalent power for this system is the same as the back vertex power, which is 20. All right, so the D equivalent power is also 20 diopters. All right, now I want to figure out what this back curvature is going to be, and I can do that because I have the relationship of the equivalent power to the different base curvatures. All right, and so that equivalent power is a function rather of the front base curvature, the back base curvature, and our compensation factor, which is our thickness value, times the front base curvature times the back base curvature. All right, and so the equivalent power you just determined, that was your 20 diopters. The front base curvature was given to you in the problem as 20. This is the back base curvature, that's what we're looking for. This is the 0.010, that's your 10 millimeters divided by your 1.5 indice of refraction. The front curvature is given to you again as 0, and then this is what we're looking for here, which is the back base curvature. Well, 0 times this and 0 times this is 0. So this guy all goes away, okay? And so the back base curvature, D back base curvature, is then just going to be 20. All right, makes sense. It's kind of intuitive, but you know, back base curvature here is going to be equal to 20 diopters. But it works out mathematically also. All right, and so once again, we need to figure out where our secondary Gaussian plane, because once again, we're going to be dealing with images. All right, so it's a plus lens, so the images are going to be on this side. We're dealing with back vertex power. And so I'm not really concerned about our primary Gaussian plane for the same reasons for the first problem we weren't. So, but I need to know where that secondary Gaussian plane is going to be, and that's determined by this linear value we call E prime. And the E prime, once again, is the difference between the focal point of the back vertex power and the focal point of the back equivalent power. All right, to find the focal point of the back vertex power, I take the inverse of the back vertex power. The back vertex power, we determine, we gave us the focal point. Oh, actually, we already given that, so we can work it out again. But anyway, and so that's going to be 1 over our 20, just to do the math. And then we're going to have a plus 0.05. All right, so that was actually given to us in the problem, but we did the math backwards. But anyway, all right, so then this is the focal point of the equivalent power, which is going to be the inverse of the equivalent power. You determine what the equivalent power is. That is also a plus 20. So once again, these things are going to just work out to be the same. So it's kind of cumbersome in the math doing it this way, but it's just so you can follow along. All right, and so this guy here is going to be your 0.05 minus a plus 0.05. Wow, that's kind of kooky, and that gives me a 0. So my E prime for this thing, the location is 0. What does that mean? That means that there is no distance between the back surface of the real lens and the Gaussian surface. And so the Gaussian, the H1, is right here, or H2, excuse me, is right here, right along the back surface. And that makes sense because there's no power up in the front. It all has to come from the back. But once again, mathematically, it all works out. We want to do image size again, so we're back to our right triangle for the reasons we were talking about before. We'll draw it out here. So we have a plano lens in the front, and we have a plus, plus 20 lens in the back. Okay, and we have a thickness of 10 millimeters from here to here, and we have also determined that our H2 plane is located right on top of that back surface of the real lens. Right? We have some sort of object out here in space. We don't know where that object is located, but we're told once again that the angle subtending into the system is 10 degrees, so I know that the angle subtending out of the system is also 10 degrees. All right, so same, and our image is going to fall back here. All right, and so same drill as we did with the first problem. So I'm going to have my right triangle. Looks like this. Here's my right triangle here, and our right angle there, excuse me, and then this angle here is going to be 10 degrees, just like it was in the other problems. This, therefore, is going to be my image height, and then this is going to be the focal length of my back equivalent power, which is going to be 0.05. All right, and so the tangent of 10 degrees is going to be the opposite, which is the image size over the adjacent, which is the 0.5, which means my image size is going to be the tangent of 10 times my 0.05. Do the math for that guy there, and he comes out to be 0.0088. And so my image size, my Y1, is going to be 0.0088. And I can also do the focal length of my equivalent power, and that is going to be what we had over here, and that is the plus 0.05. All right, so that's all our data here. We're going to do the same thing we did before, and we're going to punch it into the chart over here. All right, so this is D prime V, also known as the back vertex power. The back vertex power is going to be 20 diopters. D1 is what I call the front power, or the front base curvature, and that's going to be 0. The equivalent power, the DE, is what I call EQ, and that's going to be plus 20. The E prime, the linear distance between the back Gaussian lens and the back real lens, that is going to be 0. D2 is the back base curvature, all right? And so that is 20 diopters, which we determined. The focal length of the back equivalent plane, that is a plus 0.05. And the image size is 0.0088. All right, so that is the math involved with what we have there. All right, so we can draw that picture out just like we did in the past cases, which is going to be this guy, but I'm just going to expand it because we're going to write over each other. All right, and so I have some sort of front lens here, but in this case the power is 0, and then the back power over here is 20 diopters. I have 10 millimeters from here to here. I have some sort of optical axis that's running across here. I have an H2 plane for this system that is, the value of E prime was 0, so it's right on top. All right, I'm going to put my real object out here. I'm not given the distance from here to here, but I'm given that this angle is going to see, I'm just going wherever my H1 plane is. I really don't care where that is. All right, but I know that the angle subtended into the H1 plane is 10 degrees. Therefore, I also know that the angle subtended out of the H2 plane is also 10 degrees, because once again, there is nothing between these two planes, right? So empty space, so to speak. And that is now going to create an image that falls somewhere over here. All right, and that image size for the first one, so the image size for lens number 1, right, we already had calculated that here, and that is 0.0088, and that the focal length of excuse me, the focal length of the back vertex, not the back vertex power, but the back equivalent lens was 0.05. And I'm going to draw that from here over into here. Okay, and so there we have for our first picture. All right. Now we're going to do the same thing again, but now we're going to do that for lens number 2. All right, and so for lens number 2, what's going to happen is that we're going to change that front base curvature. So the front base curvature for lens number 1 was 0. And now for lens number 2, according to the problem, the front base curvature excuse me, is going to be 15 diopters. So the front base curvature now is going to be plus 15 diopters, so significantly steeper. All right, so rather than being flat, the front base curvature is now going to be positive or curved like that. What's the back curvature going to look like? I don't know. We'll have to figure that out. We have some guesses, obviously. The constants are the same. All right, and so that is the back vertex power of the system remains 20 diopters. The thickness of the system remains 10 millimeters. The indice that the lenses are made out of remains the same, and that is 1.5. And then our new parameter is the power of the front curvature, and that is 15 diopters. All right, so now we're going to figure out, once again, find our equivalent power, and then from the equivalent power, we're going to find out what our back base curve is going to be. Our back power is going to be our back surface lens power. All right, so we're going to start out with we're going to do the same thing we've been doing all day long, and that's going to be the back vertex power is related to the equivalent power of the lens by this compensation factor. Back vertex power is driven by the front surface power. Back vertex power we know to be 20 diopters. The equivalent power is what I'm looking for, 1 minus, this is the 0.010 or 10 millimeters divided by the indice of refraction, which is 1.5, times our new front curvature, which is plus 15. All right, solve for your D equivalent, and that guy comes out to be 18 diopters. All right, so the equivalent power of this system is now 18 diopters. All right, from the equivalent system, I can now figure out what the back power is, because I know that the equivalent power is related to the front power plus the back power with some sort of compensation, and that has to do with the thickness in juxtaposition with the front power and the back power. All right, so the equivalent power you just determined, that was 18 diopters. The front power was given to you in the problem as 15 diopters. The back power is what we're looking for here. The thickness is 10 millimeters. The indice of refraction is 1.5. The front base curvature was given to the problem is 15 diopters. And then once again, I'm looking for the back base curvature. All right, so we're going to take the 18. I'm going to throw this guy on the other side. And so 18 minus 15, that's going to give me a positive value. So I know that that back base curvature is going to be positive, which means that I already know that this is going to be a biconvex lens. Its actual curvature we're going to figure out by doing the math. All right, so I'm going to do the same thing. This is 18 minus 15, and we're going to factor out the d back. And when we solve for that, you're going to do that the same way, same algebraic magic that you were doing in the past. And when we solve for the d back, that's going to come out to be 3.33 diopters. So our d back is going to be 3.33 diopters. All right, so great. Now, I need to determine, we're looking for image sizes, so I need to know where that H2 plane is, and to do that, I need to know my E prime, its linear position relative from the real lens to the Gaussian or fake lens, and that is going to be the difference between the focal length of the back vertex power and the focal length of the back Gaussian equivalent power. All right, the back vertex power is the focal length of the back vertex power is going to be the inverse of the back vertex power, which we already know. We've done that already, but it's 1 over the 20, and that's going to be the 0.05. Once again, going to be positive because that focal point is going to be on that side of the system. The focal point of the back equivalent power is going to be the inverse of the back equivalent power. Once again, we're dealing with outside the confines of the lens. We are not in the glass or plastic. We are in air. That's why you see these ones in the numerator. That's going to be 1 over the equivalent power, which you and I have now determined to be 18 diopters. I take the inverse of 18, and that gives me 0.056. And once again, that's going to have a positive value associated with it. I'm going to take these two guys and pop them in there. So that's a plus 0.05 minus a plus 0.056. Do the math on that fellow there, and when you subtract those two out, once again, this is bigger than this guy, so you're going to get a negative value, which means that Gaussian plane is going to be to the left of the real lens, which is how it's been throughout this problem set, and it's going to be 6 millimeters away. All right, so our focal point of our equivalent system is going to be plus 0.056, and that our E prime is going to be a minus 0.006. Okay, once again, that's going to be a positive front base curvature and a positive back base curvature. So we're dealing with a biconvex lens, which is what we anticipated from the way the problem was oriented from the beginning. All right, so now this over here, this is going to be the back vertex power. That's still going to remain 20. The front curvature now is, where are we here? The front curvature is now 15 according to the problem. All right, the equivalent power has now been modified to 18. All right, the E prime value is no longer 0, it's actually 6 millimeters. The back power of the lens is now plus 3.33. All right, the focal length of the equivalent system is going to be a plus 0.056. And this guy over here, the actual image size. Ooh, we did not calculate the image size. Well, look at that. Let's do that now. So we're going to go here. This is going to be our right triangle. There's our right angle. This is our angle here, which was 10 degrees. This is the image size we want. And this guy is the focal length of the back Gaussian power. That's going to be 0.056. All right, so we know that the tangent of 10 degrees is going to be equal to the opposite, which is the image size over the adjacent, which is the focal length of the Gaussian equivalent. And so I am going to have my image size is going to be equal to the tangent of 10 times the 0.056. Do the math for that, and that comes out to be 0.00 0.0099. So our y1 is going to be 0.0099. All right. And so I'm going to put that in there, 0099. Now, what are we seeing as far as a trend? We've only done 2, but let's take a look at the trend. The front vertex power, or excuse me, the back vertex power is the same. The curvature of the front of the lens is steepening significantly, okay? What's happening to the equivalent power? The equivalent power is actually dropping off in compensation for that. The H-plane has been shifted to the left, okay? To the left or in front of the back of the back surface of the real lens, okay? The D2, the power of the back of the lens is increasing, makes sense, okay? Because I now have more power there, more steepening up, or I'm sorry, has decreased. I'm going from 20 to 0 to 3.33. It has decreased significantly, right? The front of it was flat. Now I got 15 diopters here. And so to maintain that same back vertex power, I don't need as much curvature here. The position of the H2 plane, or the secondary Gaussian plane, I'm going to put a 0 in here just to keep the decimal points the same, is now shifted 56. So it's going to be over on the other side. It's FE is going to be towards this side, 56. So it's even farther away. And now the image size is going from 8.8 millimeters to 9.9 millimeters. All right. So let's do our picture again over here. And so what we have going on here now, excuse me. And so here's our original picture from our lens number 1, and now we're going to do our lens number 2. All right. And so now the E prime, the actual location of our, of our secondary Gaussian plane is going to be 6 millimeters this way. Right, so this is going to be H2. This was H2 for lens number 1. This is going to be H2 for lens number 2. And the distance between here and here is going to be 6 millimeters. Okay, how is this going to change things? Well, the focal length of that back Gaussian plane is now 0.056. All right, 0.056 is actually going to be farther down the line here. So this is going to be 0.056. So it's actually going to be longer, right? So that means that I'm going to extend this out here, and I'm going to extend that same 10-degree slope this way. So now this guy's going to be here. He's going to be drugged down the hill. So the image size is now longer. So here's the image size of our second set of lenses, and that's going to be 0.0099. All right. So unlike our first set of problems where we are actually dragging the image up the hill, making the image smaller as we went along, this one's actually making the image bigger. Okay, so we're going in the opposite direction. All right, so that was for lens number 2. Okay, and so now we're going to do the final aspect of that problem, which is going to be lens number 3. Okay, and so we're doing lens number 3, and for lens number 3, the back vertex power remains the same. That was the constant for the problem. That was the 20 degrees. You were given the 0.05 focal length, and we determined that that was a 20 diopter lens. The thickness remains the same. That is still the 10 millimeters. The indice of refraction remains the same. That is the 1.5. Okay. The front power, however, the steepness of the front curve of the lens is now increased to 30 diopters. So we started out in lens number 1, that was 0. In lens number 2, that was 15. And now for lens number 3, that is 30. So we're talking significant increases in the curvature of the front of the lens, although the back vertex power remains constant. All right, and from that we're going to need to determine what our equivalent power is, and we're going to need to determine what our back surface power is going to be, and then we'll do our focal distances. All right, just like before. Back vertex power is related to the equivalent power, and it's related by this relationship here, which is the thickness, and then because it's back vertex power, the light hits the front of the lens first. All right, the back vertex power is a constant. That's your 20 diopters. The equivalent power is what I'm looking for. This is 1 minus the 10 millimeters over the indices of refraction, which is 1.5, times the front curvature given to you for this lens, lens number 3, is now 30 diopters. All right. Solve for the D equivalent. All right. And that guy now comes out to be 16 diopters. So the D equivalent is 16 diopters. All right. From that, I can now determine what this back curvature is, because I know that the equivalent power is related to the front curvature plus the back curvature minus our compensation factor, which is the thickness value, times the front times the back. The equivalent power, you just figured that out there. That was 16. The front curvature was given to you on the problem. That is 30. The back is what I am looking for here. The thickness is the linear thickness, which is 10 millimeters, divided by the indices of refraction of the material, which is 1.5, times the given front curvature, which was 30, times the back curvature, which is the variable we want. Once again, so now I'm going to take the 16, I'm going to throw the 30 over here. What's that going to do? Well, geez, 30 is bigger than 16. So although I now have a 30 diopter front curvature, I have a positive front curvature, I'm now going to have a negative back curvature. All right, so now I'm going to have a quote-unquote meniscus lens. Right? And so we'll do the math for this. So this is where your minus is going to come from, right? 16 minus 30, obviously going to give you a minus value. I'd factor out your D back like we did for all the other problems so far. And when you solve for the D back, that's going to come out to be a minus 17.5. Ooh, that's a freaky number. Minus 17.5 diopters there. All right. I need to know where our secondary Gaussian plane is going to be. That's going to be our E1, and that's going to be the difference between the focal point of the back vertex power and the focal point of the back equivalent power. The focal point of the back vertex power is going to be the inverse of the back vertex power, and so that is the inverse of our 20 diopters, which is going to give us a plus 0.05. Same as before, because that is a constant, but we're just doing the math just so everything follows. And I need to know the focal point of the back equivalent power. That's going to be the inverse of the back equivalent power, and that's going to be 1 over the equivalent power you just found here, which is your plus 16. And that's not a plus, that's going to be equals. And so that's going to be the inverse of 16, and the inverse of 16 is 0.063. And once again, that's going to have a positive value because that is the back Gaussian focal distance, okay, as opposed to the front Gaussian focal distance. Would be the same numerical value, but a different sign, you remember? Because it's in SSRS, the Gaussian system. But once again, we're only concerned about back vertex power because we're looking for images at this point. So everything we're looking is on this side. I'm going to take these values, I'm going to stick them in here. So this is going to be plus 0.05 minus a plus 0.063. This guy again is bigger than this guy, so that's going to give us an overall excuse me, negative value, and that's going to be 0.013. All right, so our E prime value is going to be a minus 0.013. Our back equivalent power, our focal distance for our back equivalent, is going to be 0.063 over here, and then we need to know what our image size is going to be. All right, so we're back to our trusty right triangle with our 10 degree subtended angle. This is going to be our image, and then this one here is now going to be the focal length of the back Gaussian equivalent, which is 0.63. All right, so the sine of 10 degrees is going to be equal to the opposite, which is the y prime, over the adjacent, which is the focal distance of the back equivalent. And so our y prime is going to be the sine of 10 degrees times our 0.063. Crunch the math on that, and that comes out to be 0.011. So the y prime is going to be 0.011. All right, and we're going to have a meniscus shape for that guy. All right, now I'm going to take that stuff here and I'm going to stick it back into our chart that we had over here. Once again, the back vertex power remains constant. Everything's the same there. This D1 is what I call the front power, and that's 30. And once again, that was part of the problem, although it's not explicitly stated here. 0, 15, and then 30. All right. The D equivalent power, that's going to be 16. What do we notice in that pattern? Well, what's happening is that equivalent power is dropping off. All right. The E value is shifting even farther to the left. All right, so that's going to be 0, 1, 3, almost twice the distance, which means that our Gaussian plane is going to be even farther to the left. Our D2, the power of the back of our lens, which we went from 20 down into a low plus number of 3, we're now into a negative 17.5. So if we've crossed over that threshold onto the other side, all right, excuse me, and that our focal point of our equivalent power, which we determined here, that's going to be a plus 0.063. You'll notice that these values are steadily increasing, and as these values steadily increase, these guys will also increase, because this guy is now a 0.011, and I'm going to add the 0 in there to keep the decimal points. All right, so here's the same. This is the opposite pattern that we had in the past, but it follows the same pattern but in opposite direction. So in this case, our Gaussian focal distance is increasing, and when that happens, we're dragging our image down the hill, and the image is now becoming greater. All right, so I'm going to take this, and then what I'm going to do is superimpose it over our previous picture right here. All right, so there was our H2 for the first one, our H2 for the second one. All right, our H2 for the third is going to be even farther over, right? So that was going to go over this way. And so this is going to be the H2 for our third lens, okay, because the distance between now here and here is going to be 0.063. It's going to E value. That's going to be a 0.013. All right. Now all of a sudden this plus lens is now turned into a minus lens, but I'm not going to redraw the picture. All right. The relative spacing is the same. The power of the equivalent system remains in the same spot centrally. So where these distances are measured from to remain constant. All right, and so, but this guy here, the focal point of the back Gaussian surface is now 0.063. So once again, measuring from a common area here, this guy is now way out here, which means our image is being dragged down the hill even further, which means that our image size is going to be greater. And that, once again, just from the calculations we had before, that's 0, 1, 1, 0. So 1, 2, 3. That's 11 millimeters. So that is a significant increase in the size of the image. Now, what does this mean? Well, this means that image size is driven by the focal length of the back Gaussian surface, or the back Gaussian power. Right? And so you want to choose base curvatures that are going to give you a minimum amount. In this case, this has a back vertex power. This is an obvious hyperopic correction, and the problem with hyperopic correction is going to make things appear larger than they actually are. Bring them into focus nonetheless, but make them larger than they actually are. All right? And so you'll notice that as you increase the front base curvature, right, make the front base curvature steeper, you're increasing the image size, which is not what you're trying to do. You're trying to minimize that magnification effect. But also, I do not want to have Benjamin Franklin form. All right, and so once again, I've gotten to somewhere in this area. I had a 15. I had to steepen the front base curvature. That's great. At 15, that gave me a 3. But then I doubled it to 30. So the correct, or the best form lens, is going to be somewhere just, between 15 and 30, but closer to the 15 and the 30. And that'll give me the front base curvature that I want, the positive value, but that will give me a minimum amount of back negative curvature. So I will have a meniscus lenses that will fit the properties of the face and the eye movements. What I need to do, that's also the way, just to refresh your mind, that's how lenses are actually made, right? They're starting out with a blank with a set front base curvature, and then material is removed from the back. And so that is how lenses are made. So I don't have a choice in today's world to make what you would think would be a pair of Benjamin Franklin glasses. That you're going to make a lens that's going to have a meniscus shape to it. So I want to have a minimum steepness of the front that would allow me just to give enough of a negative curvature on the back. So I fit the parameters that I need, and also would give me a minimum amount of magnification, because the more that I steepen that front base curvature, the more I'm going to have those magnification effects. So that is the take-home of this entire Gaussian 2 setup. All right, and it works in both cases. Whether you're dealing with meniscus lenses or biconvex lenses, the patterns follow itself. And that was the point, like I say, when you're filling out charts like this, is to follow patterns. All right, so any questions that you have on any of this, you can post them to the discussion board for the course. All right, and I'll see you next week.